2, 1. All right. Okay, so welcome back. So resistance. Now, as you're continuing on, this is kind of for grade 11 or introductory physics side, and you're beginning to learn about circuits. So you have a knowledge of now what voltage is, what current is. Can put up the link to both. Okay, so voltage, you can take a peek at that. You definitely should understand what voltage is before diving into resistance. And if you want to be able to understand what current is, okay, so the flow of charges, okay, or electrons, I'll put up a link up above there. So those are the first two kind of introductory videos that I wanted to do. And here is the third one, okay, trying to explain to you what resistance is. Now, I'll tie in resistance with Ohm's law, okay? So Ohm was a scientist who was actually trying to measure kind of the resistance or the opposition of the flow of electrons, which really is resistance, all right? So I'll tie it in to this particular video, okay? So resistance, as I said, okay, so just a moment ago, so with respect to resistance in any kind of a circuit, so it doesn't actually matter what kind of a conductor you have, unless you have things that are called superconductors. You can certainly try to research those if you like, okay, where there is not a lot of resistance. Pretty much the hope is that there is zero. But in general, at least up to this point, we are still stuck at the kind of junction where any load, any electrical load, any conductor that we have, even a wire itself, is going to have some form of a resistance. Now, some have very little, okay, and others have a lot. Now, what does that mean? Well, resistance you can tie back in. What I like to tie it back into is to friction. Now, friction, you will think back all the way back to dynamics. No, you know that it kind of opposes motion, right? So the more friction you have, okay, the more opposition to actual motion that you will have moving forward. Now, in terms of electrical devices or electricity in general, so the flow of electrons, where we're referring to here is, in terms of this word, in terms of, instead of using friction, okay, we use resistance. This is electrical resistance. It really just measures of how much opposition, okay, that you have. So hence, friction, that there is to the flow of electrons in any kind of, a circuit or conductors, right, as you're going through. So that is what resistance is, and we want to be able to measure this. Now, so how much of that? So the more that you have, the more opposition that you're going to be working with. Now, these resistances, very often what happens, okay, is that we model them in terms of resistors. Now, we also use resistors to try to have this opposition, right, of flow of electrons. We may want to be able to reduce the amount of current, okay, that is actually flowing. So those resistors are just electrical devices, okay, that carries a set, okay, or a variable amount of resistance. So we can actually vary, okay, this. Now, there are symbols for these resistors. So in a circuit, okay, that you have, you very often are going to be running into a symbol like this, and this is actually the resistor itself. Now, if you take it in, so just before, I kind of popped it into a search engine, so there you have it. Here are how the resistors actually look like in real life, and you can see there's a ton of them, okay, that you have. You can notice that they have colors, which basically tell us, how much of resistance there will be in that device. And then hopefully, as time goes on, you can get your hands on these particular resistors so you can work, okay, with this. So now coming back here, in terms of this resistance, okay, and how it relates back, okay, so this person, the scientist, I guess, so Ohm, okay, has been interested in trying to see, what is this opposition, what is this resistance that you would have. So now, if you would carry out, and let's say that we had some kind of a battery, right? So we had some kind of a battery, so positive, okay, and negative, so whatever this might be, okay, in terms of a battery on its own, okay, or, you can use the electrical symbol for this, like this, okay, and that battery now was hooked up, okay, and it was hooked up to some kind of a load, right? So here, we have some kind of a load. Now, you're going to have a voltage, okay, across here, and you know that if you're going to be hooking this up, and if there is some voltage, there's going to be some flow of current. So we now have current, which is flowing. Now, please remember, that these are really just electrons, okay, that are passing through here. So technically from the negative to positive, but our convention is from positive downwards. So we have this current, okay, which is going to flow. So these electrons. And now we want to see, okay, so how much resistance is there? You know, how hard is it for these electrons to go from one end to another, right? And what Ohm has noticed is the following. So he would basically set a certain voltage, okay, across. And he wanted to be able to measure what the current is, right? So he was trying to see, all right, if I set this voltage, you know, what would be the current that is passing through this particular load, right? So as you're going, okay, in that direction. Okay, so what he was noticing is that as he would increase the voltage, so as he would increase the voltage, he would find that the current would also increase. And if he would be decreasing the voltage, the current also decreased. And moreover, okay, so what he concluded was this. He said that, well, these two must be proportional. Now, by the way, so this is the symbol for proportional. So proportional, okay, so within here, so that's what we have. Now, if you forgot what proportional means in terms of math, I'll put up a link up above there. So this is going to date you back a little bit, probably grade 9 or grade 10. So proportionality, okay, especially as you started to learn, okay, about, for example, straight lines, okay, and then having proportional, so linear kind of systems in general. So anyways, so this was kind of done through an experiment, and this is what he noticed. Now, if you would plot this out, you noticed something even further. So, you know, if you take your X and your Y axes, okay, so within here, now on, so this is going to be your current, you know, let's imagine your current is in amps, and your voltage, so your voltage is going to be in volts, right there. And then what he was noticing is, so if you would increase, okay, the voltage, okay, so right here, you know, keep increasing it, increasing it, increasing it, increasing it, then what he would notice is that you would have, for a set amount of a load, that your current would also increase, right? And it would increase, so as you can see here, so it would increase proportionally. Not only that, you could actually find and do a connection and kind of an interpolation and an extrapolation in here, that it would be a linear proportion that you would have in here. So it would be proportional, okay, with respect to a linear term. And now, if you recall, so if you take any kind of a line, so if this was the change in voltage and this was the change in current, right, you may remember, so this is the change in Y and the change in X, and that was a slope, right? So we had a slope, and we would refer to slope as M. So if you go back to math, well, it turns out that this slope actually gave us the resistance. So this resistance right here, so this opposition of the flow of electrons, okay, it would give us this particular constant for a certain load. Now, of course, depending on what the load might be or what the conductor is, you know, it might be more resistance, okay, or less resistance. So what it would mean is that this particular line would either be steeper, so this would mean that the slope is much bigger, so more resistance, or it would be flatter, where you have less resistance, okay, overall, so the current can flow much easier, right? So you would have this. So depending on what the slope is, that slope would actually govern what that resistance will be. Now, if you think about that in terms of your equation, so if you go back to y is equal to m times x, right? So in this here, where this was the slope in general, then our y, notice, is our voltage V, right? Our slope, okay, so he found that this was the resistance, and then our x, okay, was the actual current, right? So this is your relationship that you have. And this is a pretty simple relationship. Now, the assumption here is that, so when he was doing the tests, and this holds as long as your temperature, so as you're going through here, so as long as your temperature pretty much remains constant. Now, it can change slightly, but if it changes too much, then this relationship won't necessarily hold, and it won't be a nice smooth line, okay, a nice direct proportional relationship. But if you do make this assumption, which you do when you're just beginning all of your studies of circuits in general, okay, and in kind of foundational physics classes. So when you make this assumption, this actually holds. And this relationship is amazing. And, you can certainly go back, and if you kind of rearrange this formula, you know that resistance is going to be equal to nothing else but the voltage divided by the current that you have. And you can find out what that resistance will be. So, for instance, okay, if you're going to be doing this, so here's maybe one example. So if somebody tells you that, you have, let's say, a battery which is, 12 volts as you're going through, and then you measure out, and maybe the current, okay, is, 25 milliamps, okay, so for example, so that's what you would have in here. You can find out, and you can substitute exactly what would be the resistance. So this is just 12 volts divided by, now be careful, you have to change this back, so the assumption is that everything is in metric standard units. So you would be changing it back, and that change from milliamps would change back into amps. So this would have been 0.025, and that would have been now in amps. Okay, and if you substitute this back in here, so 12 divided by, so 0.025 equals, so this would tell us that the resistance is 450 volt per ampere. Now, due to the fact that Ohm has been working on this, so like a lot of the things, like for example, we measure voltage in volts, right? Due to Volta, okay, who was the scientist. Okay, so the current, okay, is in amps due to Ampere, okay, another scientist. Well, here's another scientist that worked on this. So instead of using volts per amp, well, we refer to this as ohms. All right, so this is ohms, okay, within here, again, named after Ohm. And the symbol, so this is a direct kind of different symbol. So this has, okay, the symbol of ohms in this way. All right. Now you can, okay, so I do my ohms in this way. You can certainly utilize, okay, the symbol. So that the symbol itself is a little bit nicer, okay, than I draw it. So it's kind of like this. Okay. So as you're going through, you have your ohm symbol, okay, in general. So it has a very distinct look. All right, so there you have it. Okay, so here's the kind of equation that we have. Now, if you wanted to remember, okay, the relationship between voltages and currents, and then you have a certain amount of resistance, I, to this day, okay, still remember this. Instead of writing as V is equal to R times I, okay, I actually remember it as Vir, right? So V is equal to IR. So this is a little bit easier to remember. You can sometimes use a mnemonic for this. So I've seen this kind of in textbooks. So this is, a very important resistance, right? But I do remember literally as VIR. So even when I kind of think back, I always write it in this way. Okay, instead of having the R in front, okay, I put the I in front, just so that it's easier for me to remember. But the equation, of course, doesn't change. You can swap them back and forth. All right, okay, so that is it. Okay, so there is your Ohm's law, okay, or Ohm's equation that you have. Again, please remember that the assumption is that the temperature doesn't necessarily change. You can think of resistance in terms of just friction, so it's definitely very closely related. The more resistance you have, the one thing that you will find, as much as we may want to keep the actual temperatures constant, things are going to be heating up if there is resistance, same way as there would be with friction. So there's a transfer of energy from kind of electrical energy back into thermal energy, okay, and then heat might be dissipated in some forms. You definitely do see this in, for example, incandescent light bulbs. Now, many of you may not see those anymore because we primarily use LEDs, so much more efficient in transferring energy to light, okay, instead of having a lot of inefficiency, okay, and transferring it to kind of heat that you have. So there you have it. I hope that you found this useful. I'm going to start getting into now circuits and then trying to figure out how to actually work out circuits find out voltages, find out currents, work with various resistances, both in series and in parallel, so that you can understand these concepts. Thanks for watching. See you in a future video. Bye, everybody.